My name is Jens Roland. I'm a professor of ecology at the University of Alberta in Canada, and I'm going to talk about a long-term study of population dynamics that we've been doing on Alpine Parnassius smintheus butterflies in the Rocky Mountains of Canada. There are 5 species of Parnassius in North America: Evers manni, Phoebus, Claudius, Berrii, and Parnassius smintheus, which has by far the broadest geographic range of the 5 species from the southern Yukon in the north, south to New Mexico. And like elsewhere, Parnassius smintheus is dimorphic. And they're characteristic of open and semi-open meadows in the Rocky Mountains of Canada and the United States. Larvae feed on succulents, Sedum lanceolatum. Adults nectar feed. They will nectar feed on sedum as well, but also on a wide variety of alpine flowers. Now, alpine habitat being patchy can result in fairly patchily distributed populations and isolated populations simply by the nature of their structure, and also are subject to weather extremes, both spatially, north-facing and south-facing slopes, for example, and temporally, among years and within years. And from a conservation perspective, these two characteristics may be of concern with respect to habitat loss and habitat fragmentation, and also to potential effects of climate change and extreme weather events. And our population dynamic studies since 1993 are in part designed to address that. As I mentioned, the range is quite widespread across North America, and we've been studying them at a site roughly in the middle of their range at Jumping Pound Ridge, Alberta. And I've been doing that in collaboration with Steve Matter, Dr. Steve Matter at the University of Cincinnati and his students, Dr. Nusha Kigabati at Western University and her students, and Sherry Founds at the University of Alberta. With respect to the population ecology and conservation, the two things that we are particularly interested in is the potential effect of rising tree line in the mountains due to climate change and its effects on dispersal and gene flow. I won't talk much about the gene flow in this talk, and also climate and weather effects on population dynamics. Jumping Pound Ridge is about 8 kilometers long, with meadows of varying degree of connectivity, either long open meadows, small isolated meadows, and being varyingly connected or not connected through the effect of intervening forests in the saddles that occur between those meadows. And the data that I'm going to show you throughout this talk comes from mark recapture studies of the 21 subpopulations over 29 years, and involves about 42,000 captures of 24,000 individuals. And this through a network of these 21 individual meadows. So the study of movement has been done primarily using mark recapture techniques. And this is of interest because tree line has been rising at these sites. If you look at an aerial photo of our study site in 1952, you can see meadows were largely open and connected with each other, large, whereas even by 1993, meadows were much smaller because tree line has risen and are varyingly connected or disconnected by intervening forest among those meadows. And our interest in the mark recapture work was to see whether individuals marked in various meadows moved into other meadows, depending on how much meadow habitat there was between those pairs of meadows and how much intervening forest, to see whether forest either prevented or at least reduced the rate of dispersal among habitat patches. These are our results. We marked individuals in all the meadows, as I mentioned, and the data here are the number of recaptures in other meadows among those 29 meadows, so meadow pairs in this case. And you can see we got a lot more recaptures if meadows were close to each other than if they were distant. And if that distance was through open meadow, we would see individuals move up to and more than 2 kilometers. So quite a bit of movement through the meadow component of that landscape. When we considered the amount of forest between meadow pairs, we never saw any movement beyond 1 kilometer. And the steepness of this resistance to movement was much greater for forests than it was for open meadows. So clearly, not only do forests prevent movement, but they also reduce the rate at which individuals move between meadow pairs. And as tree line rises, then potentially there's less and less movement among meadow pairs. This loss of movement could have effect on population dynamics in that dispersal could be an important component of the synchrony of meadow pairs and the degree to which synchrony might help either maintain regional stability or potentially lose the stability on a local scale. And what we wanted to do here was look at whether the dynamics that we see through time, although they are correlated to some extent among all 29 meadows, they are also different from each other to a certain extent. And what we found was that that correlation in population growth was quite high when populations were close to each other. And that correlation declined the further and further two meadow pairs were from each other. So if dispersal is a synchronizing element in the dynamics of these, that loss of movement at greater distance might be acting to reduce the synchrony of subpopulations. And the important thing here is to note that if we just look at the effect of distance through forest, it's a much steeper effect on the loss of that synchrony among meadow pairs. And this would, again, support the notion that this loss of dispersal is producing this loss of synchrony among meadow pairs. Therefore, within this rapidly changing landscape, we are seeing that the intervening forest is limiting dispersal more and more. And this could potentially reduce the rate of recolonization if some of those small populations went locally extinct. And it could also limit access to resources by butterflies, either access to nectar plants, larval host plants, or potentially to mates. Secondly, it looks like the increasing amount of forest acts to decouple dynamics between pairs of meadows. And this could act to increase the risk of local extinction in that a small meadow may be decoupled from surrounding meadows and increase the risk by which individuals go extinct and its ability to get recolonized from adjacent meadows. This loss of synchrony, though, it has a larger, potentially an effect to reduce the risk of regional extinction in that the dynamics might be independent, more independent among subpopulations, and that ensures that some populations will persist. The second thing I want to talk about is the potential for weather affecting the population dynamics of Parnassius smintheus. And the data I'm going to show are based on the density estimates we have each year, based on mark recapture data, and the rate of change from 1 year of adult population to the population the next summer. And we use the rate of population between those two as a measure of population change and the potential effect of weather on population change. The population is only measured at the adult stage. We do not measure population size of eggs, larvae, and pupae. But this change between the two summers could be affected by weather at any time of year, not just the weather that the adults are experiencing. So we wanted to do an exploratory analysis of potential weather effects on rate of population change. And we wanted to do this in two ways. First, just an exploration of potential weather variables and their effects on rate of population change, and then experimental confirmation of any patterns that come out from that analysis. As I mentioned, the data are initially our population size from 1 year to the next, and that gets converted to the rate of population change between subsequent years that we can work with. And this was published in a paper that we had in Ecological Monographs in 2016. So we want to relate the rate of population change to weather in August, September, potentially October, November, December through the winter. The egg stage is overwintering. Larvae are present in April and May and into June. They pupate in June and July, and emerge in the middle of July, flying through August into the beginning of September. And it could be weather at any of these times that affects this rate of population change, not just the weather during which the adults are present. We wanted to identify which among 91 weather variables, and I'll briefly list those next, and find out which of those best determine annual population change. Basically, we're asking the question, does rate of population change? Is it affected by a number of variables? We always look at the effect of population size on rate of change, looking for density-dependent effects, but then look at a variety of monthly variables: mean temperature, mean minimum temperature, mean maximum, extreme effects, rainfall, snowfall, amount of snow on the ground, and some annual weather variables such as total summer rainfall, maximum amount of snow, and the date of snow melt. This ends up being 91 potential dependent variables, which is a lot of variables, but we have a lot of estimates of rate of population change in this particular analysis, 318. And we used two analyses to try and figure this out. The first, we used random forests, which is a regression tree type of analysis, machine learning, to try and tease out all of these variables. And this is analysis which is particularly well suited when you have lots of potential independent variables, and you need quite a large number of dependent variables. It's also very good if you suspect there may be some fairly complicated interactions among these variables, and it may be able to tease those out. We also subsequently looked at mixed effects models based on the variables that we found to be quite important in the initial winnowing of variables using random forests. Random forests determined that the most important variables tend to be dominated by weather in early winter. November, mean temperatures, extreme minimum, extreme maximum, the amount of snowfall, etc. And so we use those variables as a subset of the 91 to further explore their effects in mixed effects models, and found that it was the November temperature and November snowfall variables that determined the magnitude of the population change best. And of course, in this case, we also included subpopulation as a random effect on the analysis. And what we found was particularly important was an interaction term between temperature and snowfall. And this had by far the biggest effect on the model and in explaining the rate of population change. And you can see this very nicely if you look at satellite imagery of, this is just one of our meadows. This is Meadow H in two different years, 2008, 2013, both taken on November 25th. In a year with very little snow, it was a negative population growth. The population declined between the previous summer and the following summer, roughly 20% survival. And a year with lots of snow where the population was positive, roughly increasing fivefold in adult numbers from one summer to the next. So this visually shows very nicely this effect of snow cover as an important variable in affecting rate of population change from adult populations from one summer to the next. Based on these exploratory results, we conducted a series of experiments on overwinter egg survival to confirm that this in fact was important. And we did a 7-year experiment in the last 7 years, part of this time series, with where we wanted to look at overwinter survival of the eggs, but also experimentally manipulate snow cover to see whether that affected the egg survival. Was that the mechanism by which population changed? And this experiment was done with 3 aims. First, to obtain independent data on the effect of winter weather on egg survival. Secondly, determine the importance of overwinter survival of eggs on generational population growth. Is survival of eggs correlated or related to growth, population growth? And then also to identify the importance of winter weather on the egg stage relative to weather in other seasons, the larvae, the pupae, and the adults. And the technique that we used was the planting of eggs across one meadow where we have a gradient of snow cover, typically. From the forest edge where we get a lot of snow out into the middle of the meadows where typically the meadows are clear of snow, so the spatial effect of snow cover. And also have done it across 6 winters, some with lots of snow, some with very little snow, and some with intermediate amounts of snow, and thereby estimate egg survival from the experiment in each year and try and relate that to the estimate of RT for the populations each year, that is based on the adult numbers from one summer to the next summer. How important is egg survival in explaining that change in adult numbers? Eggs would be very difficult to find under the snow, clearly, or even at the end of the winter. So what we did is we used fine mesh little cages that we rolled eggs into, placed them on the ground where eggs are normally laid by the adult females, and marked those locations across the meadow with a snow stake, a gradated snow stake. And we also placed a temperature recording hobo recorder at each of those locations. These replicate sets of plantings were put out in September and recovered in May and scored for successful hatch. And hatch is very characteristic on the eggs of these, where the caterpillars have successfully chewed their way out of the eggs. Here are the results. On the x-axis, this is the proportion of egg hatch in each of these different winters, 6 different winters. And this is the overall network RT for the populations between subsequent summers, pairs of summers, the intervening winters between pairs of summers. And you can see there's quite a strong correlation. The higher the egg survival, the greater the population increase, and lower egg survival resulted in negative population decline. And the R squared in this is quite high at 82%. So egg hatch is explaining a very large proportion of the change in population change for this butterfly. We also wanted to remove the effect of snow by placing some replicates of eggs above the snow line. Snow does not get particularly deep, up to maybe a meter or so, but we placed some up in trees where they were not protected by snow over the winter to see how their survival compared to those that were under the snow to some extent. And in those same years, the eggs that you place above the snow line, indicated by the red dots here, often showed 0 survival and some, or at least reduced survival of the eggs when they are not protected by snow cover. So what these studies have indicated is the rate of population change from one summer to the next is highly correlated with overwinter egg survival. And if you remove snow cover, egg survival is reduced to near 0 in most years. And these results are consistent with the observational data, the statistical modeling from the random forest and the mixed effects models that we did in winnowing down all of the potential weather variables that could be affecting population, providing a strong indication that overwinter effects dominate the dynamics of this butterfly. So snow cover is extremely important for egg survival. And this is this could be an important component of climate change. Many mountainous areas are receiving less snow with climate change. Overwinter egg survival is also the main component of generational population change. It dominates the dynamics of Parnassius smintheus. And this implies that possibly weather effects on larvae, pupae, and adults and on fecundity may have little consequence for the dynamics compared to the effects of weather on the eggs. And this may be a consistent pattern for other species of Parnassius, which would be interesting to try and identify. Similar lifestyles, you might expect to have similar effects on the life stages of the other Parnassius species. So is there a trend in populations? Is climate change having an effect on these populations? Well, actually, there's been a general slight increase in abundance over the 30 years that we've been studying these butterflies. And most years, or sorry, there have been more years with positive population growth than with negative growth, but the pattern is fairly small. But there's been no major decline in populations of Parnassius. If anything, a slight increase. Is there a conservation concern for Parnassius? Shrinking habitat is a potential concern. Obviously, if we lose habitat, that's that would be a concern for conservation. And although we haven't seen a weather effect on the long-term dynamics, multiple years of lack of snow could cause quite dramatic declines in populations. And as the frequency of these type of years increases, that could be a potential concern. And thank you for your interest.